In this chapter, we'll take some of the ideas we learned about equilibrium and we'll apply them to situations involving acids and bases. The first thing, let's review what exactly is an acid and what exactly is a base. And we'll learn some formal definitions after this. So an acid, we know is sour tasting. This is things like a lemon. You know, they can react strongly with metals, generally tarnishing them. They'll change blue litmus paper to red, and they feel burnt, like a burning sensation on your skin. Bases are bitter tasting, things like baking soda. They have a very soapy feel. They change red litmus paper to blue, and they generally speaking do not react with metals. And there's a few definitions of acid and base we'll learn in this chapter. The first one is an Arrhenius acid and base. So a substance that dissociates in water to produce hydrogen ions, H+, is an Arrhenius acid. A substance that dissociates in water to produce hydroxide ions is an Arrhenius base. So here we have HA reaching equilibrium in water to give us H+ and A-. So the important thing here is the dissociation into H+. And then we have MOH, where M is a metal, such as sodium, will dissociate into water to give us M+ and OH-. The important thing here is to remember that the Arrhenius definition of acids and bases only applies to aqueous solutions. Okay, so if we're in an aqueous solution, we can apply this definition. The next definition is the Bronsted-Lowry acid and base. So a substance that can transfer a hydrogen ion, in other words an H+, is a Bronsted-Lowry acid. This is also known as a proton donor. Substance that can accept hydrogen ions, H+, is a Bronsted-Lowry base. In other words, this is a proton acceptor. So a proton donor, Bronsted-Lowry acid, and a proton acceptor is a Bronsted-Lowry base. And when we talk about a proton, what we're talking about is simply H+. So if you think about hydrogen, and you think about removing one electron, you're left with H+. Hydrogen only has one proton, one electron, and one neutron. So if we take that electron away, effectively what we have is just a proton. Okay, so that's commonly referred to in acid-base chemistry as a proton. So a base, according to Bronsted-Lowry, is a proton acceptor, and an acid is a proton donor. Okay, so the proton donor, the acid, will transfer the proton to the proton acceptor, the base. So you end up with BH+ and A-. What's interesting, though, is that in solution, it's very unlikely to find H+. And this is due to the high reactivity of the hydrogen ion, the proton. So it's actually hydrated by one or more water molecules, and most commonly we refer to this as H3O+. So H+ and H3O+ are interchangeable. So you'll never find H+ on its own. You'll always find it as either H+, or H3O+, excuse me, or you would have multiple waters hydrating the proton. But generally speaking, we'll focus on only H3O+. Okay, but understand that it could have 2 waters, 3 waters, 4 waters. Okay? And we refer to this as the hydronium ion. So H+ and H3O+ are synonyms, just like proton and the hydronium ion. So these are all interchangeable because we're all talking about the same thing. Okay, so we're talking about the proton, H+. And it becomes the hydronium ion when it meets water. Okay, and down at the bottom we have a note that H+ and H3O+ are used interchangeably, and that's true. Okay, so let's look at a proton transfer reaction. So here we have HCl, a strong acid, combining with water to give us Cl- and H3O+. So what exactly is happening here? Well, what we have happening is that we have a proton in red, and that proton is being accepted by water. So in this case, water is acting as a base. So these electrons will come and grab this proton, kicking these electrons back to Cl minus. So what we end up with, or back to Cl. So what we end up with is Cl minus, and now our proton in red is here, attached to a water, to become a hydronium ion. Okay, so we're left with Cl minus and H3O plus. Okay, and that's illustrated with bubbles down below. Another form of proton transfer could be to a base, a weaker base, like ammonia. So here we have the same process. So we have the lone pair on nitrogen attacking this proton to kick these electrons back to chlorine, and we end up with NH4 plus, the ammonium ion, and Cl minus. Okay, so notice that the proton in red is now attached to ammonia to become the ammonium ion. Okay, and that's illustrated by the space filling model down below. The next one, we can actually have water donate a proton this time. So now water is acting as an acid. So we saw water act as a base. Now we're seeing water act as an acid. Okay, so here ammonia is again acting as our base. So these electrons can come steal this proton, kick the electrons back, and we end up with OH minus, because if we kick this electron pair back onto the oxygen, it will leave it negatively charged, so we have OH minus, and our red proton is again attached to ammonia to give us the ammonium ion. Okay, so two definitions real quick. So we have amphiprotic and amphoteric. Amphiprotic means that it can donate or accept a proton, things like water, for instance. Amphoteric means it can act as an acid or as a base, again, things like water. And different ions can act as acids or as bases. Some of them may be amphiprotic, and some of it may be amphoteric, depending on which acid and base definition you're using. Okay, but just make sure we understand both of these terms. So one means it can accept a proton or donate a proton, means it can act as an acid. One means it can act as an acid or a base. And many times these terms go hand in hand. But it depends on what definition of an acid and what definition of a base we're talking about. And that will probably make more sense once we get deeper into the chapter. So in many acid-base reactions, we can establish an equilibrium. So this is where the ideas that we learned in the last chapter about equilibrium start to come back in. So in general in an acid-base reaction, we have a proton donor, proton acceptor. So we have HA, we'll call that the acid, B, which is for the base, BH plus, which means after the base has accepted the proton, and A minus, which means after the acid has given up the proton. Okay, so here we have an H plus donor and an H plus acceptor. Then we go through a reaction and we end up with an H plus donor acid and an H plus acceptor base. But notice what's happened. So now our acid, our acid, has now become A minus, which means that now it could reaccept a proton. Our base has now become BH plus. So now it has an extra proton that it could potentially give up. Okay, so this is our equilibrium. So we can see this reaction. So maybe we have a lone pair here grabbing onto this proton, forming A minus and BH plus, or maybe we have this lone pair grabbing this proton to give us back B in HA. Okay, so that in that way, that's how our products can become our reactants, and our reactants, how they become our products. So for the forward reaction, HA is the proton donor. And for the reverse reaction, now we have BH plus as the proton donor. Okay, so that's how they swap roles, and we get this equilibrium. Another definition, which is a conjugate acid-base pair. These are chemical species whose formulas differ only by one hydrogen ion. So the word conjugate comes from the Latin conjure, which means to join together. So now our HA, which is our H plus donor, our base, our H plus acceptor, again becomes our BH plus and our A minus. So this B, our base, and our BH plus, our protonated base, this is a conjugate acid-base pair. Because we have a base becoming an acid, or becoming its conjugate acid is the way we refer to it. So this would be our conjugate acid-base pair. We also have a second conjugate acid-base pair, which is our HA, our acid, and now its conjugate base, which is A minus. Okay, so those two things together are a conjugate acid-base pair. So you can think of the conjugate acid or the base as what the acid or the base from the forward reaction become after the reaction. Okay, so here it wants us to write a balanced equation for the reaction that occurs when phosphoric acid, H3PO4, donates a proton to water to form a dihydrogen phosphate ion. Okay, see if you can write out this reaction. So go back and kind of look at what happens in acid-base reactions. See if you can write a reaction for this. Okay, so let's take a look at this one. So it's just asked us to write the basic acid-base reaction that occurs when H3O plus donates a proton to form a dihydrogen phosphate ion. Okay, so start from writing what we know. So we know that we're donating a proton to water. Okay, so we know that we have H3PO4, or acid, reacting with water. So that would be your reactants. Now we want the acid to give up a proton to water. Okay, so we know one of our reactants will be H3O plus. So now all that's left is to write out what our other product would be. Okay, so just simply remove a proton from H3PO4 to make H2PO4 minus. Okay, that's your dihydrogen phosphate ion. Okay, and that's the whole reaction. And just make sure you label your states. So obviously things like acids will be aqueous and your water will be a liquid. Okay, now to ask us, is a dihydrogen phosphate an acid, a base, or is it amphoteric? So take a look at our dihydrogen phosphate ion. Ask yourself, is that an acid, a base, or is it amphoteric? Okay, if you answered amphoteric, you're right. And why? Because I have that negative charge out there, that lone pair that could take in a proton. But it also still has two acidic protons that it could give away. So it would be amphoteric. Okay, now it wants us to write a balanced equation for the reaction that occurs when the cyanide ion, Cn-, accept a proton from water to form hydrogen cyanide. Okay, so in this one they tell us we're reacting cyanide ion, Cn- with water. So those will be your reactants. So Cn- plus H2O. And we know that we're transferring a proton from water to Cn- because of this negative sign, can come grab a proton. So that'll be our base, our acid. Water will be that would be our base, water will be our acid in this case. Okay, so we end up with HCN and OH minus. Now it wants to know, is Cn minus a Bronsted acid or a base? Okay, so I kind of just gave this one away. We know it's a base. Why? Because it's accepting a proton. So it's using that negative charge to go take a proton from water. So in that case, water is acting as an acid. Okay, so it says in the following reaction, identify the acid on the left and its conjugate base on the right. So first, find the acid, and then see if you can identify the conjugate base. Okay, so hopefully you recognize HNO3 as an acid. And now what we need to do is find its conjugate base. So this just means look for what it would become if it gave away a proton. So looking over here to the right, the only thing we can see would be this nitrate ion. Okay, so this would be our conjugate acid-base pair. Okay, then our second conjugate acid-base pair, which it doesn't ask us to do that, but if ammonia is acting as a base, that means NH4 plus the ammonium ion will be our conjugate acid. It didn't ask us for that, but there you go. Okay, so what about acid-base strength? So we know that some acids are strong acids, some acids are weak acids, and we've heard of strong acids and strong bases. So here it says some acids are better proton donors than others. The more easily a substance donates a proton, the less likely its conjugate base will accept a proton. So in other words, the stronger the acid, so stronger acids, we have a weaker conjugate base. So the stronger the acid, the weaker its conjugate base. Okay, so if an acid gives up a proton very easily, its conjugate base is not likely to take it back very strongly. Some bases are better proton acceptors than others, so the more easily a substance accepts a proton, the less likely its conjugate acid will be to donate a proton. So the stronger the base, the weaker its conjugate acid. So hopefully that makes sense, because if we have a strong acid, it gives up its proton very easily, well then why would its conjugate base want to accept that proton back if it was given up so easily? Okay, so if we have a strong acid, we have a weak conjugate base. And if a base accepts a proton very strongly, then its conjugate acid isn't likely to give it up so easily. Okay, so strong acid, weak conjugate base. Stronger base, weak conjugate acid. Okay, so let's look at a couple definitions again. So strong acid. So what exactly do we mean by a strong acid? So this is an acid that associates 100% in water and exists in solution only as its conjugate base. So if we have HA plus H2O, it'll go completely to completion. So this is not an equilibrium arrow, it's just a completion arrow, to give us H3O plus and A minus. So if we were to take a look at this, so the red bar represents our acid. If we put it into water, we'll completely lose HA and we'll end up with only H3O plus and A minus. Okay, this would represent 100% dissociation. A weak acid, however, is an acid that only partly dissociated in water and exists in solution as a mix of the acid and its conjugate base. So here we have HA plus H2O in equilibrium with H3O plus and A minus. Okay, so if again the red represents HA, our acid, when it dissociates into water, we end up with some HA left, some H3O plus, and some A minus. And depending on the ratio of this will depend on, or the ratio of this will depend on how strong or how weak of an acid we have. So if it's a stronger weak acid, quote unquote, then we'll have more H3O plus and A minus. If it's a weaker weak acid, we'll have more HA. And a very weak acid is an acid that does not dissociate in water and exists in solution only as the undissociated acid. So even though it's capable of being deprotonated, just putting it into water does not dissociate. So HA plus H2O, and here we have only a reverse reaction arrow with H3O plus and A minus. So it does not form H3O plus or A minus at all. Okay, so strong acid completely dissociates to H3O plus and A minus. Weak acid only partially dissociates, and then a very weak acid does not dissociate at all, or very, very, very small amount. Okay, so here's just acid-base strength chart. Okay, so just notice things like HCl, for instance, hydrochloric acid, very strong acid, but notice extremely weak base, Cl minus. Okay, so the strong acids will always have weak conjugate bases. And our strong bases, like say OH minus, always have a weak conjugate acid. Okay, so you can kind of look over these on your own, to get a kind of a feel for some strong acids, strong bases, but notice we have things like nitric acid, sulfuric acid, hydrochloric acid. Okay, these are all strong acids. And our strong bases, oftentimes you'll see OH minus, things like that associated with strong bases. But just notice, if I have a strong acid, its base is very weak. If I have a strong base, its acid is very weak. Okay, so we can break these down into strong acids and bases and weak acids and bases. And here's a list of the strong acids. So bromic acid, hydrobromic acid, perchloric acid, hydrochloric acid, hydroionic acid, chloric acid, sulfuric acid, nitric acid. And our strong bases, sodium hydroxide, potassium hydroxide, lithium hydroxide, rubidium hydroxide, cesium hydroxide, calcium hydroxide, barium hydroxide, strontium hydroxide. So notice all of our bases have one thing in common: hydroxides. Okay, and many of our strong acids have the same thing, a very similar thing in common. So bromic acid, chloric acid, hydrochloric acid, hydroionic, again chloric acid. Okay, so what do they have in common? Halogens. We also have sulfuric acid and nitric acid. Those don't share halogens, but they're also strong acids. Okay, so the best thing to do in order to know what's a strong acid and what's a strong base and what's a weak acid and what's a weak base is memorize this list. Okay, so there's 1, 2, 3, 4, 5, 6, 7 strong acids, and there's 8 strong bases. So if you memorize those, then if it's not on that list, then it must be weak. And if it is on the list, then you know it's strong. Okay, so make sure you commit this to memory. Okay, so in acid-base equilibria, which direction is favored? So here I have HA plus H2O gives me H3O plus and A minus. So it says if H2O is a stronger base than A minus, it will favor the right side. So if H2O is stronger of a base than A minus, then it will favor the forward direction. If A minus is a stronger base than H2O, the equilibrium will favor the left side. So if this is a stronger base, in other words, it will steal this proton, then we'll favor the forward direction, or the reverse direction, excuse me. Okay, so that's how we can kind of come to in our minds which side the equilibrium will actually lie. Okay, so in other words, in every acid-base reaction, the equilibrium favors transfer the proton from the stronger acid to the stronger base to form the weaker acid and the weaker base. So the stronger acid and stronger base will always take control over the weaker acid and the weaker base, no matter which side they're on. Okay, so the reaction itself doesn't care whether we write it as reactants or products. Okay, so it's always going to be the stronger acid and stronger base taking over. Okay, so the next section we'll talk a little bit about the autoionization of water. Okay, and so since water is amphoteric, one water molecule can donate a proton to either water molecule to another water molecule. And this is called autoionization. So this is one water molecule donating a proton to another water molecule. Okay, and this is autoionization of water. So that just means that here we have water acting both as an acid and as a base just inside of water itself with no other outside influence. So that means even though we always refer to water as H2O, what we actually have in a sample of water is OH minus and H3O plus. And this is always occurring. Okay, so it's always going back and forth. Okay, so it's always going from H3O plus to OH minus and back and forth. Okay, so it's never just as H2O itself. Okay, even though it can act that way, in all reality, in a solution of water or in a sample of water, you have OH minus and H3O plus. And this is due to the autoionization of water, simply because it can act as an acid or a base. Okay, so if you take two water molecules and react them, you get OH minus H3O plus. Okay, and we can say that the equilibrium constant expression for the autoionization of water is equal to what? So it's equal to our products, just like before. So just like our equilibrium constant before. Kc is equal to concentration of OH minus times the concentration of H3O plus. And remember, the H2O terms, we don't use them because, or we don't include them because they're both water. So remember, pure liquids and solids are not involved in our Kc value. So this particular Kc value is also known as Kw because it refers strictly to water. So Kw is equal to the concentration of OH minus times the concentration of H3O plus. And at 25 degrees C, the concentration of OH minus and H3O plus is equal to 1 times 10 to the minus 7 molarity. Okay, so that means our Kw is equal to 1.0 times 10 to the minus 7 times 1.0 times 10 to the minus 7. So Kw is equal to 1.0 times 10 to the minus 14 molarity squared at 25 degrees C. Okay, so that's Kw, basically just a constant. So this means that in aqueous solution, OH minus and H3O plus are inversely related to each other, meaning that as one goes up, the other goes down. So if Kw is equal to OH minus times H3O plus, and when that's equal to a set value, that means if one value goes up, the other one has to go down. And so that also means if we know the value of one, we can calculate the other based on Kw. So if we, for instance, know the concentration of OH minus, we can calculate H3O plus. If we know H3O plus, we can calculate OH minus based on the Kw. Okay, so the concentration of H3O plus would be equal to Kw over OH minus. In other words, 1 times 10 to the minus 14 molarity squared over OH minus. And the concentration of OH minus would be equal to Kw over the concentration of H3O plus. Okay, so in a neutral solution, we have equal parts H3O plus and OH minus. In acidic solution, since we have protons being donated to water, we'd have more H3O plus than OH minus. And in a basic solution, we would have more OH minus than H3O plus. So here it wants to know what is the OH minus and H3O plus concentration in a 0.0012 molar solution of sodium hydroxide at 25 degrees C. Okay, so based on what I just told you, see if you can come up with this answer. Remember that sodium hydroxide is a strong acid. That's important. So if you can't remember quite what I mean by that, go back to the definition of a strong acid and see what you come up with. Okay, so let's take a look at this. So the first thing, we know that sodium hydroxide is a strong base. I think I said strong acid before. I meant a strong base. Okay, so sodium hydroxide is a strong base, so that means the concentration of OH minus will be equal to the concentration of sodium hydroxide that we put in solution. Since it will completely dissociate, then we know that the two concentrations will be equal. Okay, so remember that H3O plus, or the concentration of H3O plus, will be equal to Kw over OH minus. So if we know the concentration of OH minus, all you have to do is plug that in. So 1 times 10 to the minus 14, sorry, this should be a superscript, times 10 to the minus 14, so just your Kw value, over, so I'll put a little caret in there. There we go. So the concentration of H3O plus will be 1 times 10 to the minus 14 molarity squared over 0.0012 molarity. So if you do that math, you end up with 8.33 times 10 to the minus 12 molarity. Okay, so that's the two concentrations we're looking for. So we got OH minus right off the bat. We had to do a little calculation for H3O plus, but easy enough just using our formula for Kw. Okay, in the next video, we'll talk about the pH scale.